But they're not.
I guess I'm gonna have to shout. It's 4 o'clock. Time to start the festivities. Today we have our very own Katie Seraphin. Katie's assistant professor here in the department since 2019. She has a BA in environmental studies from Connecticut College. There's an interesting fun fact about that coming up in a minute. Prior to grad school, she worked at the U.S. Geological Survey, St. Petersburg Coastal and Marine Science Center for a while. So she has no excuse for not knowing what she was getting into when she came back to Florida. She has an MS and PhD in Ocean, Earth, and Atmospheric Sciences from Oregon State University. So you go from Florida to the other corner. And she did a postdoc at Stanford University Department of Geophysics and the Stanford Urban Resilience Initiative. She was actually recently selected as a 2021 UF Early Career Florida Climate Institute's faculty fellow for her contributions to interdisciplinary climate research extension and education program. Her research focuses on extreme sea levels and coastal flooding and erosion hazards to better understand how our coastlines are changing and the resultant consequences for people and places. Now, we have 2 fun facts about her.
Who?
One, she's a twin.
That's 2 of me.
Anyway, that second fun fact, she played basketball mixed
Yeah.
at Connecticut College, not to be confused with the University of Connecticut.
Not UConn.
Power in women's basketball. She's actually 5th or 6th overall in the school records for total points scored, total rebounds, total field goal percentage, and total free throws made. Yeah. Whoa. And so talk today about Florida risk transfer and the consequence of climate change and infrastructure modifications along the San Francisco Creek, California.
Yes.
Take it away, Kate.
I figured that science was really my calling, not basketball. What's Division 3? One more fun fact that Mike didn't mention. I didn't share this with him, so he doesn't know about it. I actually did apply to UF for graduate school when I was at St. Pete, but in the geological sciences department. So my calling to geography hadn't come through just yet. So when I volunteered to give this colloquium, beginning of the semester, I thought I would use it to kind of push forward some of the research that I have been trying to work on and move forward since moving here and starting this position here. But when push came to shove and I had to provide Josh with a title and abstract so he could make those really great fancy flyers that we see out in the hallway, I kind of fell back on this project that I began at Stanford during my postdoc position, working with Dr. Kosef, Baker, and Zuccali, because I thought that some of the themes discussed in it really had would really interest a broad set of folks in the audience. Some of you may have heard me talk about this during my job talk in 2019, but this work has come a long way since then, and I'm really proud of where it is. A lot has been done. And I will also say, kind of, I guess this is evidence or proof, some unsolicited advice to all the graduate students in this room. It becomes a lot harder to finish something when you move on to a new position. So let that be some advice. I started this work in 2018, and now it's kind of finding its way to hopefully soon being published. So communities across the nation are grappling with how to mitigate flooding along urban rivers with aging infrastructure and uncertain changes to the climate. Today, I'm going to share with you how infrastructure modifications that could be overall beneficial to a system might also have unintended consequences, using the San Francisco Creek as a case study. The San Francisco Creek is located in the South San Francisco Bay. It flows and originates at the Searsville Dam and Lake up in the Santa Cruz Mountains and flows about 22 kilometers into the South San Francisco Bay. And so that means flooding along river can be influenced by both ocean or bay-driven processes and inland precipitation and river-driven processes. The river flows through 5 different municipalities. It's a border of 2 counties, and it's been entwined in issues surrounding habitat conservation, sedimentation, and flood control for many decades. So you can imagine what a jurisdictionally complex river this is to manage. Also, there is a sharp gradient in wealth that aligns with the direction of the flow in this river system. And so the green areas indicate places where the income is higher than the median household income for the county, and pink areas indicate areas where it's lower, income is lower than the median household income for the county. This location has flooded drastically before, which here is depicted in blue. And the flood of record occurred during an El Nino event in 1998, and it impacted thousands of properties and caused millions of dollars in damage. The majority of the flooding occurred at this bridge. Let's see if my laser pointer works barely on these other ones, highlighted in red. And I should say that all these kind of like gray lines are different bridges along the river system. And so the majority of flooding occurred from this bridge here. And if you're not familiar kind of with how flooding might occur around bridges, this bridge has the lowest capacity of all bridges along rivers. So that means the least amount of water can pass through it. So you can imagine if the flow becomes really high and you have kind of a small hole for that water to get through, instead of being able to pass through it, it backs up behind the bridge and can break out and flood over the banks of the river. Since that event, a number of changes have been proposed or have taken place to reduce these flooding hazards. There is a project downstream called the Reach One project that's kind of highlighted in this green color that focused on widening the channel. So there's a golf course and a lot of marsh in this area. And so you can see from this photo on the bottom, really widening the channel, creating these very large flood walls along river, and also increasing the bridge capacity of that Highway 101 bridge that down river at the upper extent of this Reach One project. And so this Reach One project occurred in this downstream lower 2 kilometers of the river. Now there is focus on this other project called the Reach Two project, which looks at this kind of more upstream 8 kilometers of the river here highlighted in yellow, and is specifically trying to mitigate flooding from this location where there was so much breakout flow during the 1998 El Nino event. And some of the modifications to the river that are being focused on right now are increasing the bridge capacity where we had the most constriction of flow, widening the channel in places that it can be widened, which is not as easy here because it's a very urban river with lots of homes right up on it. And then having some top of bank treatments to avoid overtopping. And so the next question you might ask yourself, well, okay, we have all these different modifications we might make to the river. So how do we decide how high to build one, right? Well, if you're not, or to answer that question, we first have to think about, well, how do we how do we understand the spatial elevation of water levels along river? And to do that, the water level is really based on your flow condition, the depth of the river, the width of the river, right? So there's these other kind of geometric characteristics that matter for dictating how high the river is. And so typically, one of the ways that we would decide kind of, how to build how high some water level is that we would create a design event. And so just a show of hands here, how many people have heard of the term return period or recurrence interval? Yeah, a lot of people. And so really what we're looking for is an event that is rare enough that it doesn't happen all the time, right? So we're kind of dictating some acceptable level of risk, but also that is kind of financially feasible to be able to build to that level, among other kind of, some characteristics that might be important. And so traditionally, for kind of flood mitigation projects or flood mapping, the way we would do this was first get observations if your river is gauged of discharge or flow at some location along river, hopefully at your kind of upstream boundary. Fit those extreme discharge events to a model, calculate return periods from that model. So, we only have a certain number of extreme events. They're rare, right? So they're more difficult to characterize. So we can fit a model to that data to then be able to extrapolate beyond what we know about our observations and maybe extract the 100-year event, an event that has a 1% chance of occurring in any given year. We then would take that event and we would put it into potentially a river model where then the characteristics of the river come into play, and we'd be able to understand from that extreme flow condition how high the water levels might be. And if you have locations along river where the banks are lower than that, you maybe would want to build something so that water can't overflow in those areas, right? So that is how kind of you would choose how high to build. For this case, for this upstream project, the design event that is being chosen is the 70-year event, or it approximates a 70-year event. And so it is a flow condition very similar to this flood event of record. And there are a number of reasons for choosing that. One, because financially it's too expensive to build protection to higher levels, but also people have opinions when you're building things in their backyards. And so right now that is kind of the plan for a lot of this infrastructure modification, that we're looking at flooding, protecting from flooding up to the 70-year event. And this is a very traditional way to think about flood mitigation projects in different areas. And so we can begin to ask some questions though, right? So however, by evaluating and designing for a single event, what might we be missing? What locations might flood in slightly worse conditions that we're not necessarily considering because maybe there's some higher level of risk we don't care about? How might a changing climate increase the likelihood of flooding, right? A lot of times we're not necessarily including projections of climate in some of these infrastructure projects that are going to persist and last for many years. And then finally, what false sense of confidence might we be giving to people who live within the vicinity of the river who aren't necessarily as knowledgeable about kind of the risks of flooding and what these probabilities mean? And so we begin to answer some of these questions in this project by using a modeling framework where we merge statistical and numerical models to think about a large ensemble, large range of potential flooding scenarios. And I'm just briefly going to go over these methods. But what we do is we take synthetic statistical estimates or modelings, probabilistic estimates of joint ocean and river conditions. We pass them through a hydraulic model to get kind of that spatially varying water level along river. And then with that, we can get statistically robust estimates of the probability of flooding at everywhere along river that we're interested in. And this framework has been published in 2019 in my Natural Hazards and Earth System Science paper, which I went back to look at. And I guess if you're in the geographic thought class, you maybe will have to read that paper at one time. But Kaylee told me today that either the paper was so not memorable that she doesn't remember reading it, but that week was skipped.
That was not skipping.
Something happened.
We will already read it this year, so you can place it on the wall.
Look at that. So that's a framework, and if you want to get more information about this method, it's in there. I'm also working with a team from the University of Central Florida under the, it's funded by the U.S. Coastal Research Program, and my graduate student Samantha Timmers just graduated working on that. Now, Bree is also part of this project, but we're taking this methodology and turning it into a more generalizable framework so it could be applied more broadly across the United States. And so that paper that kind of updates some of these modeling techniques is in revision right now, but will be published soon. Okay, so we'll briefly go through each of these, but again, the framework, you can get a lot more information about it, and some of you, I guess, already have a lot more information about it. So if we first kind of dive into the synthetic modeling, what we're trying to do here is we want to get many different physically plausible estimates of combinations of bay and river discharges that we maybe haven't seen in our observational record. Because the records here that we have at this station are only about 20 years long. And so you can imagine that events are rare in general when you're looking at extremes, but then if you're looking at how extremes combine, or maybe even how an extreme combines with a non-extreme, or two moderate events combine, right, we don't have a lot of co-occurrences. And so the idea behind these synthetic estimates is to not only extend our records to get many different joint estimates of extremes, but at the same time also make sure that we capture the dependency between those processes that exist and the interannual and seasonal variabilities as well. And so what these figures show, in both of them, the observational data is in orange red, and the one example simulation of 10,000 years of daily maximum conditions is in black. And so the left-hand side shows for storm surge. So when we're simulating this coastal water level, there's a storm forced component, and there's also a tide, more deterministic component. And the storm force component is what's going to have dependency with our discharge storm events, right? Not the tide is deterministic. And so we first can see that if we look at the, for this one example simulation, our distributions, our cumulative distribution functions of the observations and simulations look pretty good. And then the dependency between the two processes is also captured with this modeling technique, which you can see here with this scatter plot of storm surge on the x-axis and discharge on the y-axis. On the right-hand side, what we also want to capture is kind of this seasonal variability. And I should also mention, in this modeling technique, we're not trying to model one specific event perfectly. What we're trying to do is capture the statistics, right, of our processes well. And so here, this is just a zoom in of 10 years of time series of synthetic record, where we have river discharge on top, storm surge in the middle, and then the coastal water level, so the storm surge with the tide on the bottom. We can see that our simulation, this one example simulation and observation, also kind of represents the seasonal variability and interannual, so the fact that we have different extremes in different years. Well, and so this method gives us, all those different combinations of extreme and non-extreme events that we could think about, how they might be driving differences in water level. But that's only our boundary conditions. Now we actually physically have to put these through a model to get our along river water level growing. And so the next thing we do is set up a hydraulic model. And so here we're using HECRA's, the Hydrologic Engineering Center's river analysis system. And we're using a 1D steady flow implementation of this model. And our upstream boundary of the model, so where we input that discharge, is this yellow star. It's about 12 kilometers upriver, and it's where the river gauge, where our data is. And then the downstream boundary, there's not a tide gauge or water level observations at the coastal end of the river, but there is a tide gauge up in Redwood City, about 12 kilometers north, that is a reasonable representation of the storm force and tidal water levels in this area. And so we use that gauge as our downstream boundary. If you're familiar with HECRA's models, what we're going to do is you basically output a water surface along all these different transects, which have information about the banks and the depth of the river channel and frictional coefficients. And we have about 590 transects for 12 kilometers of river. And so we have, there's about a transect every 20 meters. And so this is a very highly resolved river. There are bridges in this model. And if you are a HECRA's, you know a lot about river modeling, There are levees in the model, so we do allow overflow out of the model. So if flooding occurs somewhere, water is lost to the system and less water moves downstream. Now, you can imagine if we're going to create all these synthetic simulations, right? It might be computationally prohibitive to run them all through this model. So what we essentially do is create models of models. We use surrogate models to model the output from HEC-RAS. And so at every single transect, what we basically do is, we run a certain set of conditions through our model. Okay, and so for this case, you can imagine this plot here refers to this specific transect along river. So in this, we ran 900 boundary conditions that represent our sample space well. And then we essentially can get a coastal water level at that location for all of those different conditions. Well, then we can use a function, and in this case, we use a scattered interpolation function to fill in the blanks for all the other conditions that we haven't physically modeled through HEC-RAS. And what that allows us to do is, rather than physically running this model over and over and over again, every time we have a different condition we want to know a water level for along river, we can just get that simulation, which maybe we have a coastal water level of 1.3 meters and 21 cubic meters per second discharge. That would be a water level here. We do it at all transects. And maybe we can get a water surface elevation along river that looks something like that. Then we roll our dice again. We get another estimate of a 3.5 meter water level and a 415 cubic meter per second river event. That would put us somewhere up in this upper right-hand corner, and then we can get a much higher water level along river. And so I already told you we have one synthetic simulation of 1,000 years that is daily maximum conditions, right? And so that's basically what this figure shows here. Each one of these gray lines is from that synthetic simulation and represents a different transect along river, where your downstream bay is on the right-hand side, your upstream is on the left-hand side. So this is a long river distance on the x-axis, and your elevation or water level is on the y-axis. And so what this allows us to do is efficiently extract along river water levels for any upstream and downstream boundary condition at any transect along river. And we don't only have to do that one time, right? We can do that as many times as we want to. And so not only can we get an understanding of at a transect how many times the water level might be over a levee or a bank during that 1,000 year simulation, we can kind of embrace the uncertainty of our modeling techniques and do this many times to get many different estimates. And in this case, we're estimating flooding by calculating the probability of flood initiation. So I'm not actually mapping flooding here. What we're doing is looking at a specific transect, okay? And then we're looking at how many times or how likely it is for, in each one of these different simulations, our water levels to kind of exceed that transect. So at every transect, we can calculate a probability of flood initiation. Okay, so this allows us to then explore flooding hazards for all different kinds of river configurations, right? We're interested in thinking about how the infrastructure might play a role in modifying flooding hazards. And so the first river configuration we look at is the baseline scenario, and that is the present day river configuration with that REACH 1 project accounted for. The next is an infrastructure scenario that includes all of those REACH 2 projects that I spoke about, increasing the capacity of the Pope Chaucer Bridge and changing some bank elevations along river in that more upstream extent of river. And then there's one more river configuration that we look at. I mentioned to you that there is a dam at the top extent of the river, where the river originates, or the creek originates. And that dam has essentially filled to capacity over the last few decades. So I'm just going to show, or sorry, the lake has filled to its capacity. over the last few decades. So it's lost almost all of its capacity. And so I'm just going to show you some aerial images. Here's one from 1948. There's one from 1991. Maybe you can kind of see it. One from 2007, a little brighter. And then one from 2018. And I will kind of just outline what that original extent was in 1948. And so Stanford owns this dam, and right now we're working with different management strategies because it essentially provides no flood control because of how filled it is. And also it's really, for years, been mucking up some of the natural habitat for salmon in that area. And so the top infrastructure modification they might make right now is to poke a hole potentially in the bottom of the dam and basically let sediment flow out to the bay for many years. What that would do would essentially remove the sediment, infilling some of it from this area. A lot of the fines would flush out and be beneficial for the marsh and maybe flush out to the bay, but you could have sediment landing along river and changing the depth, which could change flooding hazards. And so the last scenario we consider are these infrastructure modifications with what we're calling, or what Stanford calls a no action scenario, where we kind of let all this sediment kind of flow out over a long period of time and look at where it lands and don't do any management of that sediment. Okay. And so these are the different river configurations we're going to look at, but we also know that the climate is changing. So we also have 4 different climate conditions that we're going to consider when thinking about this interplay of infrastructure and climate. Just looking at my time. And so the first condition synthetic simulation we use is one that represents present day conditions. Okay, so we just want to get better estimates of how events could combine and cause flooding. Next, we consider a scenario where we increase the variability of river discharge by about 50%. And this value is based on some of the observations that have of variance increase in precipitation for this region over the last few decades. We also consider a scenario where we increase sea level by 30 centimeters, and that is kind of a low to mid-range projection for this, for mid-century for this area. And then finally, we look at a scenario where we increase both of those, right? So kind of like our worst case scenario with these specific climate simulations. And what this allows us to do is now have many different estimates of different infrastructure, different river configurations with different climate conditions. And so almost this large ensemble of flood risk along river. Okay, so that was a lot of setup. And now I'm going to actually get to the interesting results from this work. Although I find this all very interesting, obviously. Okay, so what we find is that infrastructure really kind of dictates where flooding might occur. And so the likelihood of flooding at any river location varies due to river channel and infrastructure modification. So I'm going to walk us through this figure. On the x-axis, we have the along river distance. The right sides are downstream and the left sides are upstream. The y-axis is the probability of flood initiation along river. And here we're just going to focus on the left bank of the river because the left and right bank are slightly different, but the patterns are very similar. We're looking at present day climate conditions, and the 3 different panels represent our 3 different scenarios for river configuration. So our baseline, our infrastructure in the middle, and our infrastructure plus sedimentation on the bottom. The lines, the dark blue lines, represent the average likelihood from all of those synthetic simulations, the average probability of flood initiation. And then the shading around it indicates the range, right? So maybe you have one synthetic climate where you've got a lot of really extreme events and it has a lot worse flooding scenarios than other ones. And so that kind of shows how bad it could be range or how good it could be. And then this yellow line indicates that design event. So, or the probability of that design event. And anywhere this flooding from our ensemble crosses that yellow line, there's a star, and that shows that if you modeled the conditions during the design event, that's where it would show it floods. Okay, if it's below that line, you don't see that flooding by just modeling this design event. And so if we look at this top panel, the baseline scenario, what we see is there's the largest likelihood of flooding upstream of the Pope Chaucer Bridge. And I realize I didn't tell you what the dashed lines are. The dashed lines are all the bridges along river. Okay, and so the highest area of flood risk, where you have the largest likelihood of flooding, is right above the Pope Chaucer Bridge. And you have a 2.5% chance, basically, of flood initiation in any given year. And that might not seem a lot. I wrote down my conversion metrics because risk compounds, right? And so really, if you think about this over 30 years, which is about the lifetime of a mortgage, right? That actually is about a 50% chance, rather than just a 2.5% chance of flood risk. Okay. And so what we see is that the infrastructure modifications do what they're intended to do, right? We get rid of flooding if we look down at our infrastructure scenario. And if you were to integrate the flooding across all of these different transects, you would find that the infrastructure modifications actually reduce the probability along the whole river of flood initiation by almost 50%. So it does have a lot of benefits, right? But at the same time, you can see that it also redistributes what remains downstream. So now we have this flood risk, although at a much rarer kind of risk, right? It's a lower probability of flood initiation. Now in the vicinity of these downstream areas, which didn't have that same flood risk previously because so much water was lost up here at this bridge. And one thing I want to point out is if you look at the yellow line here, right? If we only are modeling this design event, we're never going to see the fact that flooding might occur at more extreme or rarer events at these downstream locations. If we look at this bottom plot, this kind of shows the same story as the infrastructure one. This is the infrastructure with sedimentation, but flooding is a little bit exacerbated, and you have some areas where flooding emerges, like down here between kilometer 2 and 3, because of sedimentation shallowing the depth of the river. So let's contextualize these results and think about, well, who might this flooding impact, or this probability of flood initiation? It's our proxy for flooding. And so I'll bring you back to the map that I showed you earlier. And again, we're thinking about left bank flooding. So that's, I talk left bank as if you're looking downriver, the left side. So we'd be looking at this upper side of the map. And here now what we're looking at is that solid blue line you saw on that top plot. Now that average probability of flooding at every transect is plotted as a circle, okay? And the larger the circle, the higher the frequency of flooding. So small circles mean rarer events and large circles mean larger frequency. And it's just written, it's the probability of flood initiation as an annual exceedance probability. And so if we look at this flooding at the Pope Chaucer Bridge, where we had the majority of breakout flooding during the 1998 El Nino event, we see that it is mostly impacting a lot of higher income communities. But if we move to an infrastructure scenario, we see that that risk is now, right, redistributed downstream to lower income communities. And I again will point out that the flooding here, or the flood risk here, right, it is rarer. So it might not occur as frequently as if we look at the scenario where before we remove the infrastructure, before we increase the bridge capacity. But we're also now dealing with communities that may not have, may not be aware of flood risk if they weren't at as high of a risk previously, but also may not have the means to recover from such an event. We can also look at the infrastructure plus sedimentation scenario, and this really tells a very similar story to that of the infrastructure modifications, but you see that some new flood locations emerge. And this one here is interesting because that's right near the Highway 101, which is a major highway. And this kind of gets into thinking about kind of damages beyond and impacts beyond just private property, where a lot of this, the river system itself appears private property. And down here we have some more, public impacts. Okay. So this shows us this flood risk transfer spatially based on our present day conditions. But what if the climate changes? And here I'm really going to show you just one scenario, which is an increase in discharge and sea level. And what you might notice, I'm going to toggle back and forth between these two. Here, we're just going to look at it for the infrastructure and sedimentation. And I apologize that they're not exactly on top of each other. But if I just toggle back and forth, you can see that our dots get bigger, right? And that means that the flooding is becoming more frequent. And so not only are we transferring some flood risk downstream, but if the climate does potentially change in the future in the ways that we are assuming it might, or that we are modeling it might, then you could have an increase in flood risk to these areas that maybe, we weren't necessarily intending. And so what this does, these dots basically are becoming about 2.5 times more frequent. So that would be turning like a 100-year event into a 40-year event. So we can kind of quantify all of this change to flood risk using a flood amplification factor. And this is used a lot in thinking about how, especially like coastal water levels. If we're worried about planning for future coastal water levels, maybe we want to know how fast our water levels will amplify or our flood risk will amplify. And we calculate an amplification factor by taking the annual exceedance probability, so that the annual exceedance probability from our climate scenarios and dividing it by our annual exceedance probability of our present day baseline climate, present day scenarios. And we do this for both the physical process, so the river discharge, right? We said that we input a river discharge and it gets us a water level along river. So we might assume that then any amplification or change to this process would have a one-to-one change with our flood initiation. And so we kind of look at answering that, or thinking about if that is true, by also calculating this amplification factor for the flood initiation at our different transects along river. Of course, we don't get flooding everywhere, so we only look at places where flooding does occur. So now I'm going to show you a plot that has a lot on it. Oh, and what we find, before I show you that plot, is that the probability of flood initiation amplifies at a faster rate than the physical process does. So in this case, there is not a one-to-one amplification of what you can call the driver of flooding, so coastal water level or discharge, and the actual flooding that occurs. So now I'm going to show you that plot. Okay, the x-axis is this annual exceedance probability, so that the probability of that value that we're looking at. The black indicates the probability, the y-axis is the amplification factor. The black lines indicate the physical process, and the blue colored lines indicate the flood initiation. And what we see, the difference between those are the difference in the amplification factors. And so we can see at this downstream boundary, we have a huge amplification of our coastal water level because we are increasing the mean of that, essentially. We're just adding 30 centimeters to our water levels there. But because there already was this large downstream flood project, we can see that there is hardly any flood initiation here driven by that change in the coastal water level. There's a huge difference between these two amplification factors. And I will say this is for specifically looking at along river flooding. For the discharge, what we see is the flood initiation, so where it floods along river and how that might change with a change in the physical process, actually increases at a slightly faster rate than that of the discharge alone. And so typically, when we're thinking about how the climate will change, we assume that just understanding that process will tell us something or will dictate exactly how the flooding might evolve as well. And that is not the case for this area. Okay, so that kind of concludes me showing you all of the results from this project. And I'm just going to briefly summarize and end with kind of, well, what can we do about this? What can we think about? So in summary, joint simulations of coastal and river process can clarify how climate change impacts and risk mitigation benefits, or can clarify the climate change impacts. Wow, I can't read this right now, can I? Clarify how climate change impacts the risk mitigation benefits of infrastructure projects. This is what I get when I have to read something. I'm too off the cusp, I guess. Planned infrastructure modifications provide benefit by removing that probability of flood initiation upstream and reducing the probability of flood initiation along the entire river. But the remaining of flood initiation is redistributed to low-income communities. The total risk reduction along the creek entails both a spatial redistribution of risk, but also an uneven decay of flood mitigation benefits over time. And so that we can think about, even though this flood risk transfer is really small under current climate conditions, maybe it's so rare, you know, it's not something we need to prepare for in the same way. The conditions would continue, the flooding would be amplified if the climate changed. For example, if the discharge increases along river from increased precipitation. And then finally, the amplification of future discharge or coastal water level may not match the amplification of the probability of flood initiation. And so this work obviously has insights that, you know, we could say, well, so what? That's great, but maybe there's some broader insights that we could apply to other river systems besides just this one. And so I like to think about them as actionable insights. What does this tell us? How is this meaningful in a more broad context? Well, infrastructure choices made today will persist for several decades, and climate change will have a profound impact on where and how it floods. And as we show, using one event for river management may really create blind spots on the risks posed by both less frequent and more frequent events, right? We do see this, or I should say, if we fail to acknowledge some of these risks that could be experienced under different scenarios, you know, there might be some areas that we're not intending. There might be consequences that are really unintended. At the same time, it might not be possible for all communities along river to benefit equally, right? So transparency in potential risk transfer can really be a valuable step towards developing flood mitigation approaches that are conscious of climate change and equity concerns, right? If we look at a broad range of scenarios, we can be transparent about the risks, even if they're small risks, but then it starts a conversation of how those risks might evolve in a changing climate, rather than just thinking about one design event where we kind of might assume that flooding won't impact it. And finally, the choice of the design event or other metrics used to assess flooding should potentially be based on consequences rather than the probability of the physical drivers. So we should be thinking about metrics and how those metrics might change and amplify rather than just that top-down approach, right? When we're looking at how climate might change, only the climatic or meteorological drivers that influence flooding in different places. But there's so many other features along river that actually are the main influences of flooding beyond just the climate forcings. And so you might be like, oh, good, she's finally done. But before I finish, I want to kind of talk about where are we now on this project in the sense like what's happening at the San Francisco Creek. Well, this Reach 2 upstream project is moving full steam ahead. The final environmental impact report was finished before I actually moved here in September of 2019, and they had all their open commenting. Arborist reports, people really care about trees in their backyard. So those are all completed in April 2021, and the project draft was completed in August 2021. And as of last year, the San Francisco Creek Joint Powers Authority, which is the governing agency that manages the rivers, which was developed after the 1998 El Nino event, and the Army Corps of Engineers are partnering through a continuing authorities program for a feasibility study where the federal government might pay for a large chunk of this project to be done or cost share it if they find that it is feasible and necessary. And I think that there is also some good news here. If we think about this actionable insight, it doesn't matter so much for like tenure in my position here, but you know, we have had the Army Corps of Engineers contacting us about our study. We've shared our study with the California Water Board, who governs a lot of the management decisions and approves projects too, who have concerns about equity and the distribution and flood risk transfer as well. And so this, even though, you know, and we have been also in communication, obviously throughout the lifetime of this project with the San Francisco Creek Joint Powers Authority and the Searsville Stanford team that is working on the Searsville Lake and Dam project, and because that's where a lot of our models came from also. And so despite this being done in an academic setting, it has the potential for some real world impact on the way things are being done in this particular community. So now I'm done.
Plenty of time for questions. We'll let somebody else ask the question. I have a technical question.
Sure.
Thank you for your presentation. It's very memorable. So I mentioned the different scenarios in your model output, and I wondered if you plan to do model validation to see if maybe one of the scenarios that you might like in the future, obviously, the future would like doing the validation of this model output.
So when you say validation, do you mean, right, because there's a lot of different components. Do you mean validating the flooding scenarios? Do you mean validating the HECRAS model? Do you mean validating the climate conditions? What, all of it?
Sorry, I'm like, I don't know. I guess seeing if like certain areas are flooding more than others, like actually on the ground level.
Yeah, I see what you mean. So I can say right now, right, the locations that we see where flooding is initiated, right? So we're not modeling flooding. Where flooding might be initiated are the places right now that do flood or are likely to flood in those certain scenarios. And so we can look at past events, and that is also how the HECRAS model is validated for thinking about, well, those past flood events. But right now, those infrastructure modifications in the Reach 2 project upstream, those haven't been completed yet, right? And so what we see wouldn't necessarily be able to be validated for that scenario until those infrastructure modifications were made, and if we had an event that was very, very, very rare, right? And so there are some aspects of this that would be very difficult to, I guess, validate in the sense that we're trying to look at things that aren't going to happen often and hopefully won't ever happen, especially if we can manage this river appropriately. And so there hasn't been a major flooding scenario at these locations since, or downstream locations since that was put into place, but there haven't, since that Reach 1 project was finished, but there also haven't been as rainy, wet seasons either. Like the last bad, really rainy, wet California was 2017, if you might remember in the news, Oroville Dam overspilled then. And so that was before this Reach 2 was created, and there was some flooding in those downstream, but still it wasn't high enough to flood the San Francisco Creek and other places. Yeah. Sadie first, and then Tim.
So when you're like in the room with Army Corps and you're saying, hey, you know, this might shift risk to these other neighborhoods, is it the Army Corps that's gonna worry about like the one bridge, or are they actually gonna worry about something that we call like climate equity or, you know, justice issues? Like who worries about that the most, who's in the room making the decisions?
Yeah, that's a good question. I don't have a definite answer on it. I will admit that the U.S. Army Corps of Engineers did not contact me, but they contacted Jenny, who is one of my collaborators on this project. I know that for, you know, I have a friend that works at FEMA, and for hazard mitigation projects, when they pay for them, there is a rubric for thinking about equity concerns. How much that is weighted, how much that is necessary in different sites, I think it's not weighted as much as economic cost benefits. I know that the California Water Board, because I have been in direct conversation with them, they say that that is one of this thinking about risk transfer to and potentially disproportionate impacts to different communities is something that is a metric that they look at, and that is when they read our paper, one thing that they were concerned about with this project. Tim.
I just had a question. Have you guys at all thought about using extreme probability distributions, trying to model them and parameterize them, and then look perhaps how those distributions have changed? Like you get a best fit distribution of a given location, and another, you know, to see how they've changed over time. You got a lot of data at the back end on this quite a few years. Maybe you can try to like parameterize and fit, you know, whether we use a Gumbel distribution or whatever distribution might fit, and then take that as the model, and then you can see how it's been changing over time at different locations. It's like, I mean, because you're doing that kind of essentially
Yes.
with a simulation,
Yes.
you know, right?
But so are you saying to do that with the simulation data, or you do it with the observational data?
With the observational, that's where it fits. What kind of
Yeah, so two answers to that
yeah,
question.
yeah.
The first is the synthetic modeling that we do. We actually do treat the extreme events separate from the non-extreme events. So we use extreme value theory, and we use the peak over threshold approach and generalized Pareto distributions. And so for the discharge and the storm surge extremes, we are taking, fitting them to non-stationary extreme value models.
Okay.
Here, the non-stationary that we are including is seasonal variability, because that is what was significant. There's no significance with climate indices for interannual variability. There was no significance with long-term trends. And it's interesting you bring this up, because this, also real world for everyone, this paper has been rejected twice. And I'm working on a rebuttal now, but one of the reasons it was rejected is because they thought we were calculating non-stationary trends of the changing climate on 20 years of data, and they said that we can't do that. And I'm saying, well, we're not doing that. But they, you know, to look at a climate change signal in the discharge, or in the sea level over a 20-year period, it's, at least for the variability of discharge, really not long enough to capture some of that variability or climate change signal.
How about you thought, if I understand correctly, the Hector's model is with the 1D model, 1D simulation, right?
Yeah.
So it's like you are simulating the water level to mimicking the flood or the flood in particular point. But if I consider about the spatial distribution of flood, because you said some places are very economically viable or important and some others are not. So did you have any thought about to see the spatial variation of the floods, now considering maybe different kind of models?
Yeah, that's, I mean, a great question. And I think, you know, part of thinking about moving this work forward is to eventually create these surrogate types of models for two-dimensional and thinking about flooding. Obviously, we're adding an extra layer of complexity in, right, in doing that. And so kind of because we were throwing so many different things at this with so many transects, and this was a new application in the model where we actually allow flooding, like water, to leave the system. We're just not actually mapping where it's going. But you bring up a good point. I'm just gonna, I'm gonna mess up. Maybe I'll just, I don't want to mess up the, gonna have to go back real far, the Zoom part. I want to pull up this map of flooding from, okay, we can look at this here, right? And so what we see during this event, we lose a lot of water, and this kind of is why Kadir's point is so important. We lose a lot of water at this Pope Chaucer Bridge, right? And depending on the topography of the area, it's not just going to flood right in the vicinity of the bridge, right? That water can move to a lot of different places. And if that flow volume is really high, that water can move to many different places. And so just because we're saying there's higher flood probability up here, it doesn't mean it's only going to impact those communities. It could very well impact communities in other places as well. And so that's why this flood project is very beneficial. And so that kind of shows some of the reasons why actually thinking about the spatial variability of the flooding and you know, kind of how it flows over the topography would be really important too for truly understanding this, any flood risk transfers that might exist. Any questions?
You answered my technical question when you answered Tim's question. Do you have any recommendations for what you could do, what the managers of the river could do to mitigate the equity problems that are going to come up from this?
Right.
Based on what your simulations did and everything, what can be done?
Right. Well, I think if we look at the results here, we're removing flooding from a more frequent event. So this is important if we want to go through with these modifications. I think, like I said at the end, transparency is key in educating communities, right? A lot of people think, oh, we're out of the floodplain, great, we don't have to buy insurance, that's what we want to do. And we don't think about these rare flood risks that could impact. And so I think one of it is saying, making it very clear that there could be rare flood events that affect other places. You could also kind of design a way and say, okay, just in case this other location, if we have a flood risk transfer, we could just build up higher in some of these areas to protect against that, right? We could have I guess, spatially uneven risk level that you're looking at across the kind of river. But I don't know that that's necessarily the answer either. I think something that's really important in continuing climate conversations is adaptable and flexible mitigation, right? Because there is a lot of uncertainty and we don't necessarily always know how the climate is changing. So in what ways can we maybe do something that then it could be reevaluated 5 years down the line, 10 years down the line to provide better protection if we do start to see some of these trends. I will say there are other projects that I didn't really focus heavily on that are being discussed for even more upstream reaches. And some of that has to do with creating kind of flood retention ponds. And so not as much water goes straight into the river because there is a lot of open area north up here near the dam, but also on Stanford's properties. And so they are also considering these other techniques that when they kind of poke the hole in the dam, also having other retaining places that will either move water in a different way downstream or will kind of reduce the flood peak hydrograph because we're capturing water somewhere else and it will more slowly flow through the system. And so here we're only touching on, you know, just a few of these configurations. There are many other different infrastructure scenarios we could potentially be considering.
I think you should import a bunch of beavers upstream and have them build beaver dams and have it to hold back the floods. It works, actually.
I mean, as a beaver from Oregon State University,
That's
I
right.
would agree.
So you know there are beavers out there.
Yeah.
So I was wondering how important is the coastal input to this region? Is it the simulations with the sea level rise scenario of 30 centimeters? How would that affect the flood amplification factors if we increase the sea level rise scenario?
Yeah, so flooding this is interesting. So Gabby brings up an interesting point, and a part of this project that I haven't really discussed, some of this project was also looking at compound flooding along river. So thinking about, okay, where you have river and ocean processes combining, where might flooding be exacerbated? And some rivers here, you can get a lot of this multivariate flooding that maybe we're underprepared for because we think about the events separately. Here, the river discharge dominates flooding. The transition zone where both processes matter is confined to the kind of the first kilometer of the river. And these infrastructure modifications, I didn't actually tell you how high these flood walls are. These flood walls were designed to withstand the 100-year discharge event and I think 1 meter of sea level rise. And so these are 10 feet high. These are yeah, I think they protect against 10 feet of flooding. And so there was a huge investment downstream. And so that could either have, right, we don't have a model that models what this was like before the Reach 1 project was put in, which I would also like to compare. But right now, that flood amplification along the river from the coastal, it doesn't affect flood risk at all because that signal never makes its way upriver because the discharge is so much more important. And so the point there is that we do so much to plan and adapt for sea level rise, right? And we're not even thinking about how precipitation might change here. And yes, sea level rise will be important. I don't want to pretend that it won't, but perhaps for flooding along this river, we should be thinking about other and investing in other climate changes, not just this coastal focused climate change. Another caveat, that's for the river, right? You still could see sea level rise here. This would need other different types of infrastructure options that I'm not taking into account when I compute that flood amplification factor. Thank you.
I think we run out of time. Next week, we'll hear from Dr. Maria Watson of the School of Construction Management here at UF. And I think that Johanna invited her, so not here.
She ran out.
Okay. So, see you next week.